Assalamualaikum and a very good morning, student. Okay, Bismillahirrahmanirrahim. I'm going to teach you about example 7.5. We're going to do some example. Okay, this example is taken from Shigley Mechanical Engineering Design book, and all the images is taken randomly from Google Images. Okay, consider a simply supported C shaft as depicted in figure 7.14. Okay, this is figure 7.14. Okay, with 1 inch diameter and 31 inches span between bearing, carrying two gears with 35 and 55 pound. Okay, this is the location of the weight, 35 pound, and this is the 55 pound. Okay, the A question A is one. We want to find the influence coefficient. B, finding total WY and total WY power 2 and the first critical speed using Rayleigh equation, and you can read all the rest lah. Okay. Okay, to solve question A, we need to find first the moment of inertia. And the question A, remind we want to find the influence coefficient. Question A, we want to find the influence coefficients. Okay, so the first step we have to find the moment of inertia given by the equation in English unit by the power of 4 per 64. Okay, which is D is given in the question is D is 1. So replace D with 1 inch per 64. You get the result I equals to 0.04909 inch. Okay, and 6 EIL. Okay, 6 EIL is given. Okay, and E is the Young modulus of steel. Young modulus of steel is 30 power of 6. Okay, 30 power of 6 PSI. You can get around 29, 30 from the textbook. Okay, also from Google you can get the Young modulus of stainless steel. You put in the value, you get the value 0.02739 pound inch cube. Okay. Okay, now we are come to these images. So I want to explain this term first, to make you understand what this term meaning. So the first one is the term D11 and the term D22 and D11 and D21. What is the meaning of this? Okay, you see here, this is the shaft given in the question. Shaft. This is a shaft given in the question. Okay, and the load is given here and here. We say that this is the load given as the load D11 and the load here is D22. Okay, D11 and D22. But how about D delta 1 2 and delta 2 1? Is it right? Yes. It means that relation between, it is a relation between delta 1 and delta 2, and also the relation between delta 2 and delta 1, meaning that you give a load here, here moving, you give the load here, here moving. It is a relation. That's why is the meaning of D11, D22, D12 and D21. Okay, so I hope you understand that. Okay, so we come to the equation. So it says that D11 equals to 24 7 what 31 minus 24 minus 7, and you get this 6EI from EIL. You get this from the previous slide, which is the value is 0.2739 times 1. No. 10. Okay. This is the 6EI. Okay, I want to tell you about this, how you get 24, how you get 7, 31, 24, and 7. It is like this, okay? 7, you see in this picture, this is 7, okay? This part here is number 7. Okay, you get the 31 minus 20 minus 7, you get 31 minus 7, you get 24. Okay, you get 24. So this come 24. Okay, then you put in the equation, then you get 31 power of 2 minus 24 power of 2 minus 7 power of 2, you get 2.061. Okay, the same goes, you get here 11. Okay, you get here 11. Here is 11. Okay, this part portion here is 11. So 11, 31 minus 11, you get 20. 31 minus 11, you get 20. So here is 20. Okay, and you put in the everything, 31 power of 2 minus 11 power of 2 minus 20 power of 2, you get this value. And then the relation between delta 1 in relation with delta 2, okay, meaning both relation with this the relation, this you get 31 minus 11 minus 7, then you get this value. Okay, I hope you understand this. Okay. Okay, when you get the value, you put it in their respective coordinates. You see here, this is delta 1, 1. This delta 1, 1. This is delta 1, 2. 1, 2. This is delta 2, 1. And this is delta 2, 2. Okay? Okay, you want to find the deflection, y1 and y2. Remember in the last video, I give you an example of this screw. This screw is represent the deflection of shaft when I activate the screwdriver. Okay, activate screwdriver, it deflect. Okay, it deflect, and this is the deflection that we want to find. Okay, so y1 is deflection 1 and y2 is deflection 2. Okay, so you give the load, you have the load given in the question 35 and also the load 55. Okay, and then put in all the value that you have obtained before, and then you get the radial velocity is 124.5.8. You see the symbol here, it might be confusing. This symbol, okay, this symbol W1 is also like, you see the, notice the differences, you might be confused. Okay, notice the differences. This is represent the weight, this is radial velocity, also like a W, like the word W. Okay, okay, from the influence coefficient, you have to find the angle radial velocity for WII and radial velocity for W22. What does it mean? Okay, you see in this graph. Okay, you remember the question figure in the question given the shaft here, and this is the load, this is the load. Okay, this is the load 35 pound, this is the load 55 pound. Okay. Okay. Given it is a bearing, okay, the bearing is moving, it's rotational, okay, and when it's moving, different velocity, okay, both, of course, it have different angular velocity. Different angular velocity. Okay. So you see, in you put in the answer is given, this angular velocity for WII for this point is 231, and the angular velocity for this point is this 140. Different angular velocity. Okay. Okay, using the Shigley equation, estimate the first critical velocity. So that may remind you what is the Shigley equation. It stated that given, if you give the load here, is the same. Give the same deflection here. If the give load here, is also give the same deflection here. Okay, let me represent to you by this. If I'm when I'm moving this my screwdriver, I give the load here, it has deflection. I give the load here, it has deflection. It have the same deflection. Okay, whether I give the load at any point, at the same load at any point of the shaft. That is the Dunkley equation. So you put in the value, you get this value 120.120 radian per second, okay, which is less than part B as expected. The idea to be extend to end body shaft, meaning that what happen if the shaft exceeds the velocity, if the angular is exceeds the velocity, maybe the shaft will fly away. Okay, the shaft will fly away. It will happen. That is why we do not want it to exceed uh, the critical speed. Okay, using the superposition method, you have learned superposition method in mechanic of material class. If you open the book Hibbeler, uh, mechanic of material book by Hibbeler, is in chapter 12. Okay, uh, this is the superposition method. Okay, you put all the value here you get, and you get the to estimate the first critical speed is like this. Okay, W equals to G is 386. May I remind you, in Malaysia, we know the gravity is 9.8. Gravity, okay, gravity is 9.8 meter per second. That is what we learn in school. Okay, in British unit, there is given by 386.1, the unit PSI, KPSI, something like that lah. Okay, that is why they used 386.1. Okay. So the final solution, the final question, we want to estimate the shaft intrinsic critical speed, suggest a modification to the Kelly's equation to include the effect of shaft mass on the first critical speed of the attachment. Okay, so for the shaft, Young modulus is 30 power of 6 psi, given for the Young modulus of steel is like that. This is the Y is the density of steel. Okay, 0.282 pound each cube, and the cross section is 0.7854 inch square. Okay, you put in the all the in the equation, you get 520.4 radian per second. Okay, we can simply add 1 per W power of 2 right side of the clear equation to include the shaft contribution. Okay, you just put here the result here. Okay, 520.4 from this and you get with the some value with less than part D as expected. Okay, the shaft first critical speed is one more single effect to add the Decalist equation. Since it does not fit into the summation, it is written up front. Okay, it's written like this. So common shaft are complicated by step cylinder geometry, which makes into inflow coefficient determination part of a numerical solution. Okay, so that's all for this video. We'll continue with the part 7, miscellaneous shaft components. Okay, thank you very much.